All right, guys, we are going to take a look at our solubility product notes. Before we start that, this is not on your paper, but it's just a quick reminder of how we work with molarity when it comes to solutions. So a solution concentration is measured in molarity as we have studied and practiced, and that is your number of moles per liter. The solution's molarity, though, relates to the ions in that solution and their molarity through mole ratios. So I have couple examples down here as a reminder. This will come in handy just as you're working in this section of the unit because we deal with solutions a lot. So when we have an example like sodium chloride, when we dissolve sodium chloride in water, it separates into its ions. Sodium is our cation and chlorine as our anion. And they're both aqueous. So the NaCl together doesn't really, this one is completely soluble, so it doesn't really exist together. So if we had the solution and it was 1.5 molar for the sodium chloride solution, then we could also say, since it's a 1-to-1 ratio from NaCl to Na, and NaCl to chlorine, that the sodium ion concentration is also 1.5 molar and the chlorine ion concentration is 1.5 molar. So everything's a 1-to-1 ratio, so it's a direct relationship there. Now, if we had something like sodium sulfide and it was a 1.5 molar solution, then if we look at this, the sodium sulfide Na2S, when it dissolves, it produces 2 sodium ions and 1 sulfide ion. So when we look at the molarity of the ions, if the solution was 1.5 molar, then the sodium would be twice that amount at 3 molar, and the sulfur would be, since it's a 1-to-1 ratio, would still be 1.5. So we're just kind of relating those coefficients. If we produce 2 ions, then we double the concentration. If we produce 3, then we multiply it by 3. Just using those ratios to help us in finding those ion concentrations, because that's really what we're going to be focusing on in this part of the unit is the concentration of specific ions in our solution. So this should look just like your notes page. So we're looking at what's called solubility product. Solubility product, or K with little sp as the subscript, so equilibrium constant. This is the equilibrium constant for the dissolving of ionic compounds in water to make a saturated solution. A solution is saturated when the maximum amount of chemical is dissolved at a particular temperature. So they might give you a temperature and say, like, this is a saturated solution formed at 25 degrees Celsius. The reason why they throw temperature in there is because if we raise the temperature, we can dissolve more ions or dissolve more solids, so it would change our equilibrium there. So we don't have to deal with the temperature. It's just that it happens at a particular temperature. So why does this have a different name? Why do we call it solubility product instead of just equilibrium? Well, we're going to take a look. So it says the following equilibrium is established when lead-2 iodide dissolves in water. So we get PbI2 solid forming Pb2 plus and 2 iodide ions, aqueous. And it gives us our KSP value. So that's our equilibrium constant for solubility, essentially. So if we were to write the equilibrium expression for this, we'd have K. We're going to use that little SP. And we'd always start, it's always products over reactants, right? So we'd start with our lead, Pb2 plus, and then we'd have our I minus, and it would be squared because of that coefficient of 2. And then we divide by, we wouldn't divide by anything. This is a solid, so it is not included in the equilibrium expression. So when we're dealing with these, we won't be dealing with anything on this left side because they're all solids. So really, we're only dealing with the products of our chemical reaction. So we can see the equilibrium is only dependent on the products of the reaction here. Okay, so the value of KSP really is just showing us how much or the extent to which something will dissolve, okay? So another thing to point out here is when we say solubility product, these two things are being multiplied here. So products are the mathematical result of multiplying something. So it's a solubility product. Now, when we look at these values, if we have a very small KSP, it's going to indicate that our chemical is not very soluble, meaning that we don't have very much ions here. If this is a small value, these are small values on the right side, so not much of it has dissolved. When we have a very large KSP, it's going to indicate our compound is quite soluble, and we would have a lot of ions on the right side. So looking at just that KSP value, we can kind of tell what's going on with our chemicals and how they are reacting or dissolving. So sliding down, we've got some general guidelines when it comes to solubility product as well. So if we say something is soluble, so if we're referring to a chemical as being soluble, it has at least 0.01 molar of an ion that dissolves, okay? It's insoluble when it's less than that, or 0.01 molar of the ion dissolves. So that's kind of our cutoff. So when we have something that's soluble versus insoluble, well, how do we determine the amount that dissolves? What we're going to be looking at is using previously learned methods, using our equilibrium expressions, in this case, our KSP, okay, formed by that. We're going to use those Rice tables again. Remember, that's our reaction, the initial change in equilibrium amount, and we're going to use those to determine the amount of chemical present at equilibrium. And there is a nice part about Rice tables when it comes to these setups, and it kind of starts forming a pattern that you'll see as we do some of these, and it kind of simplifies things for us. So it says how much of each ion for this first example of lead iodide is present when dissolved to make a saturated solution. And then we've got a couple follow-up questions. Is it soluble or insoluble, and how does this relate to our solubility rules we learned earlier this year, the NAS? So, and when we say how much of each ion is present when dissolved to make a saturated solution, this is at equilibrium, okay? We're always talking about the at equilibrium part. So let's tackle that part first. So if we have that same reaction, the lead iodide solid, and it forms an equilibrium to lead ion and iodide ion. There's two of those. We can set up a Rice table and see how much chemical we have. Now, here's the beautiful part that I love first. We can set this up. This is solid. We don't care about solids. It's not in our equilibrium expression. We do not care how much is there at all. So we know when we initially start out, we haven't dissolved anything. These would be 0. Okay, we don't know how much is changing, so we're going to use that X to represent the amount of lead that's changing, and iodide is 2 times that amount, X. Now we're adding it because it's a product. We're adding it to the product side. They're starting at 0 because we're dissolving this. So when we look at lead, it's going to be an X, and iodide is going to be a 2X. So now we want to put that into our equilibrium expression, our KSP, and solve and see what we get here. So I'm going to do that over here. We have our expression from the top. So KSP is the concentration of lead times concentration of iodide squared. So our KSP from earlier on our paper is 9.8 times 10 to the negative 9. That's a pretty small value. So that's already telling us this is not very soluble, okay? Now, lead we're going to replace with our X there. And iodide, we have 2X, and it's being squared. So let's first simplify this right side. So 9.8 times 10 to the negative 9 2x squared would be 4x squared because we have to square the 2. So we have 4x squared for this part. And then we're multiplying it by x, so we get 4x cubed here. All right, again, the next part we want to simplify. So we're going to divide by 4 on both sides. And that'll give us x cubed on the right, and it'll give us, looks like 2.45 times 10 to the negative 9. And I would keep whatever digits are in your calculator right there for now. And then we want to take the cube root of both sides. Okay, if you're not sure how to do that in your calculator, a very easy way to do it is take your 2.45 times 10 to the negative 9, take that value and raise it to the 1/3 power. Okay, so you'll hit the little caret key, and then I would put this in parentheses and raise it to the 1/3 power. That's an easy way to find the cube root of something. So our x value is equal to, I got 1.3 times 10 to the negative 3rd. Okay, so what is that number really telling us? It's telling us that the value of x, so our concentration of lead at equilibrium, is 1.3 times 10 to the negative 3rd molar. And our concentration of iodine at that time would be 2x, so 2 times that. So 2.6 times 10 to the negative 3rd molar. Okay, so this is essentially my computer's not cooperating, 0.0026. It's a pretty small value. So if we look at our other questions, we've got our concentration in our saturated solution. We've done that first question. Okay, so we're using that rice table like we've done before to figure out our products. Again, the reactant we can ignore completely, which is really nice. Simplifies our equations, allows us to calculate easier. Now, it says, is the chemical soluble or insoluble? So if we're at like 0.0026 molar, 0.0013 molar, comparing that up here, that's looking like we are pretty insoluble. Okay? Very small amount is actually dissolving. Okay, so if we're thinking about like our container with our water and our solid, only a little bit of the ions are actually separating, but most of it's staying in that solid form. Okay, and then the second part is, how does this relate to the solubility rules learned earlier this year? Well, our solubility rules, the NaAs, so N was nitrate, we've got ammonium, acetate, and the alkali earth metals. Those are the ones that are always soluble. Well, lead iodide doesn't contain any of those. So, according to our solubility rules, lead iodide would be insoluble, and according to our calculations, lead iodide would be insoluble. So they support each other, right? So really, our solubility rules were decided and discovered through these calculations, and then the rules were developed from there. Okay, so what we learned earlier this year were rules based off of actual calculations. They weren't just something to memorize. Okay, guys? All right, let's try another one. A little bit different approach here. So, what is the KSP for calcium fluoride when calcium is 2.18 times 10 to the negative 4? Okay, and this is where that idea from the very first slide, little reminders from earlier this year, can come in handy. So if we know that calcium fluoride, solid, would create an equilibrium with calcium ion and fluorine, but there are 2 fluorine. If we know that the concentration of calcium is this 2.18 times 10 to the negative 4, then 2 times that value would be our concentration of fluoride, which I calculated to be 36 times 10 to the negative 4. Okay, and these are both their molarities. So that's just an easy way of finding that concentration. Now we want to find KSP. Well, let's write our equation. We'd have calcium ion times fluoride ion That would be squared because it's a 2, and we ignore the reactants because they're solid. So that's our KSP equation. My capital K's are not looking very capital these days. All right, and we can plug in our values. So we got 2.18 times 10 to the negative 4th times 4.36 times 10 to the negative 4th, and we are squaring that one. So when I calculate these, I like to put in my number that's being squared first. So I'd put in my 4.36 times 10 to the negative 4th in my calculator. Remember to do your times 10s. Use that EE button on your calculator, so it puts it in right. I'd square that and then multiply that answer by the 2.18 times 10 to the negative 4th. So try it out in your calculator, maybe pause if you need to. I got 4.14 times 10 to the negative 11th. So that is our KSP. Oh, that looks ugly. I'm going to erase that. Let's erase that. We'll just leave it. So that's our solubility product. Again, that's a pretty small value, 10 to the negative 11th. We're moving that decimal this way 11 times. So very, very small solubility product. We can even see that from our concentrations here. 10 to the negative 4th, that's like 0.000436. That's way under our solubility. So calcium fluoride, again, not following any of our NAS rules. So it's going to be very insoluble. Only a tiny amount will actually separate into its ions. On the back of your page, let's try another one. So we're just kind of looking at different ways this might be asked or approached. So I just wanted to go over like a number of examples with you guys on this one, just because it's a lot, it's a lot of processing. All right, so what is the molarity of a solution of silver carbonate when its solubility product is 8.5 times 10 to the negative 12? So this would be the molarity of a saturated solution. Everything here we're dealing with is saturated solutions when we're given a KSP value. So we want to find our molarity of that solution, which means we need to find the molarity of the ions. Okay. To do that, we would need to know their concentrations. So we can think of it this way. Ooh, ugly. Try that again. So let's kind of see how this breaks down. We got silver carbonate solid creates an equilibrium of silver ion. There are 2 silver ions there, and those would be aqueous, plus our carbonate ion, which we know is a 2 minus charge, aqueous, and there's one of those. So let's just look at how this rice table might look, okay, if we needed one. I wrote this way big. All right, so first thing, we don't care about the solid, my favorite part. We start out initially with no chemicals before it has created the solution. And our change, we don't know how much is being added. This one will be at 2x because of that coefficient, but we're adding that to our chemicals. So 0 plus 2x is 2x, 0 plus x is x. So those are our values, quote unquote, for our equilibrium concentrations. What we do have is our equilibrium constant. So we can set up our expression and we can always plug into this expression. That's the nice thing about equilibrium. You always have your equilibrium expression as a place where you can plug things into. Oh, that was ugly. All right. So we got silver ion concentration squared because of that coefficient of 2 times our carbonate ion. Now, we have a KSP value, so we have the left side of our equation, 8.5 times 10 to the negative 12. Very small value, so that tells us that these ions are barely going to dissolve. We're going to get really small values for our molarities. So we've got 2x, and that's being squared. That's from here. And then carbonate is just x. So again, 2x squared would give us 4x squared, times x would give us 4x cubed on this side equals to that 8.5 times 10 to the negative 12th. Very similar to our example, our first example that we did. This tends to be kind of a pattern. We get this 4x cubed a lot. Now you'll get to a point where you really honestly don't have to set up this rice table to do this. If you're starting to see, okay, if it's a coefficient of 2, I'm going to have 2x. Coefficient of 1, I'm going to have 1x. I can plug those in and you can just jump into your KSP and do this without setting up this rice table every single time, okay? That's kind of the nice thing about KSP. That's why I like it. So now to simplify from here, we divide by 4 on both sides. So we get x cubed on this side. And our 8.5, 10 to the negative 12 divided by 4, I got 2.125. I'm going to leave that in my calculator times 10 to the negative 12. Because we've got to do some further calculation right now, right? We don't want to round till the very end. So now we have to do that cube root again on both sides. Again, that cube root, easy way to do it, raise it to the negative, or excuse me, not negative, raise it to the 1/3 power, and that will help you do that cube root, okay? So your x value that you should get, I got 1, there we go, okay. I got 1.3 times 10 to the negative 4 for my x value. Now that doesn't mean we're done. When you hit x, we're not done yet. We have to make sure we've actually stated the answer to our question. We want the molarity of our solution of silver carbonate. Now this again relates back to that very first thing, that first slide. So if we want the molarity of our solution, we need to know the molarity of our ions. Now, it's a 1-to-1 ratio from silver carbonate to just carbonate ion. So if carbonate ion is X, then the concentration of silver carbonate, our whole solution, would be equal. So if X is 1.3 times 10 to the negative 4th molar, that's our concentration of carbonate. Carbonate is a 1-to-1 ratio to silver carbonate. So that is the concentration of our whole solution, saturated solution. Again, not very much is dissolving. We're looking at 0.00013 molar. Very tiny amount dissolving. So we would say that this is, again, insoluble. Okay, so we're starting to see that these small KSP values, this 10 to the negative 12 on that KSP, is making this a very small concentration of our chemical. All right, let's see. We might approach another one. So this one, if 0.150 grams of copper chloride is added to 1 liter of water, will the powder entirely dissolve if the KSP is 1.1 times 10 to the negative 7th? So how do we approach this? We've kind of got two situations here. We know how much we're actually adding to the water, so we can find the molarity of this situation. We've also got the KSP, so we can find the molarity that would actually, or the amount that would actually dissolve. Then we can compare those two values and see how they line up. So let's start with the first part. We've got 0.150 grams of copper chloride. So this is added to 1 liter of water. Well, molarity is moles over liters. So the first thing we've got to do is convert this grams to moles. All right, when I did my calculation, I got 99.00 grams in 1 mole of copper chloride, which gives us 0.00152 moles of copper chloride. And we are, our molarity would be moles per liter. So if we divide by our 1.00 liters, we get a concentration of 1.52 times 10 to the negative 3rd. Whoa. negative third molar copper chloride. So that's how much, that's the molarity of the solution that we are making, or the possible molarity. Okay, this is possible. So now we're going to see, based on the KSP value, will that molarity even be made? Can we get to that amount? How much will actually dissolve here? So let's look at our equilibrium expression. That would just be copper ion, right? Ooh, not 2 plus. I'm so used to 2 plus. It'd just be positive because chlorine is negative and there's a 1-to-1 ratio. All right, so we've got this copper and chlorine. We could set up the whole rice table for this and see that we start out with 0 of both ions. We're adding some amount, we put in X, and so we get X for both of our chemicals because they're a 1-to-1 ratio. We don't have to do all of that. You could if you needed to, but we know both of these are a mystery value. We do have our KSP, 1.1 times 10 to the negative 7th. Whoa. There we go. Our copper is some amount X times our chlorine, which is some amount of X, right? They would be equal amounts because it's a 1-to-1 ratio. So we've really got on this side, I'm going to change this to just X squared because that's X times X. So if we want the concentration of each, we simply need to do the square root of both sides. So X equals the square root of that, which I got 3.3 times 10 to the negative 4th. So that means that's the concentration of our copper, and that's the concentration of our chlorine ion. Well, it's also the concentration, because everything's a 1-to-1 ratio, of our copper chloride solution. So we have the concentration of our solution here, and we need to compare it. This is our actual concentration, and we want to compare it to our possible concentration. Well, the possible concentration is larger by a whole factor of 10. So what do I mean by that? Let's look at this. Let me get a new color. This is our main part we want to compare here. If these are different from each other, then that number in front is not going to matter what it is, okay? If these two things are different from each other, they're different by an entire decimal place right now. So the one that's bigger is our copper chloride. So what we're dissolving, what we're trying to dissolve, this 1.50 grams of copper chloride, is more than can actually dissolve, which means our question, will the powder entirely dissolve? No, it will not dissolve, right? So we're looking at what's possible versus the actual amount that will dissolve. So that's how we would approach something like this. Kind of a different situation, but still using that solubility product. So it's a pretty powerful number. All right, we've got one more example. Like I said, we're just going through a lot of examples so you guys get a clear picture of it. So last example. In a saturated solution of zinc hydroxide at 25 degrees Celsius, the value of hydroxide ion is 2.0 times 10 to the negative 6. What is the value of the solubility product constant? So similar one to example number 2, similar idea. So we've got one of the concentrations. We need the other chemical's concentration to be able to do this. Well, let's just take a look at how our KSP or our rice table might be. So we've got zinc hydroxide, solid. We got zinc ion, 2 plus, aqueous, plus 2 hydroxide ions, negative, aqueous. Okay. Whoa. We don't care about the solid, right? All right, so we aren't starting with any chemical, but we do know how much our hydroxide is at equilibrium. We don't know how much we're really adding here or changing. Well, actually we do. We know that this much, 2.0 times 10 to the negative 6 hydroxide is being added to our reaction. And so the value of that is 2.0 times 10 to the negative 6th. Well, we can relate our zinc to it by our mole ratio. Our zinc ion would be half of that because it's a 2-to-1 ratio. Zinc is half. So we get 1.0 times 10 to the negative 6th for that one, both being added, right? So now that we have concentrations, we can plug them into our equation and solve for our KSP. So we'd have the concentration of zinc times the concentration of hydroxide squared. Whoa, okay. So our zinc ion is 1 times 10 to the negative 6th times our hydroxide, 2 times 10 to the negative 6th, and we are squaring that one. Now, all right, so our answer, when you multiply this out, make sure you're trying these on your calculator, like I said before. I got 4.2 times 10 to the negative 18th. Whoa. Now let's think about that number. That is negative 18. That means we're going to have 17 zeros, points in a decimal form, and then 4.2. Okay, that is very, very, very insoluble. Zinc hydroxide, obviously not a good candidate for making a solution. Barely dissolves at all. So hopefully this is giving you an idea of what these values look like. The smaller that KSP is, the less of that chemical is going to dissolve. Your solubility of the individual ions can tell you how soluble it is. We didn't really look at any of our ones that are very soluble, and it's because their values are sometimes incalculable. If everything dissolves, then it's not really an equilibrium. So for instance, sodium chloride, it's hard to find its equilibrium constant because everything really turns into sodium and chlorine, right? So a little bit harder to create that equilibrium constant when there's not much of an equilibrium there. So that gives you an idea of some of these values and how to approach these problems. So try out the practice and let me know if you have questions. Thanks, guys.